every book it could possibly be in.
Alright, number one. What is meant by the term continuous spectrum? So what does that mean? Ethan, what you got?
Oh. What is what?
Continuous spectrum.
Continuous spectrum is a spectrum of a complete array of light.
Yeah, so a natural phenomenon that is an example of a continuous spectrum is a what? This is not part of your homework, I'm just asking.
Light.
Alright, well,
Rainbow.
Rainbow! So that's the common example of a continuous spectrum, is you just see a rainbow. Now, that's natural, but we can make those in a laboratory. Alright, number three. Differentiate between the ground state and the excited state and the hydrogen atom. Alright, Chris, what you got?
The ground state, the electron is much lower than the excited state.
It's much lower in what?
Energy.
There you go. So the ground state has the lowest energy state, and the excited state is any state above that. Yes.
Now that you mentioned hydrogen, do they have a successful hydrogen bomb?
Yes, they
Yes.
do. Yeah.
Okay, now you're not the teacher, but yes, they do. Now, we have not dropped the hydrogen bomb on anybody, but we have tested it. Is it a quick question?
Is it worse than it?
I thought Nagasaki and Hiroshima were hydrogen bombs.
Those are atomic bombs, so they're not the specific type of
What's the
hydrogen bomb.
difference?
Hydrogen bombs has to do with the idea of fission. Well, hydrogen is fusion
Are they
specifically.
more powerful?
Yes.
Like, because I know there's something called like a T-star bomb, though, which is like literally.
Fusion is what's in the sun to give off energy, so you basically is taking like a little miniature sun.
It's a miniature sun.
Basically.
I know when the bomb that was dropped on Nagasaki, the inside of it was as hot as the sun.
Yeah, they didn't tell the pilots whenever they dropped it what type of bomb it was. They knew
Some
it
people were
wasn't.
blind.
You mean like in
They didn't tell the pilots?
No, like one of the pilots, like a while after, he ended up going blind because of it.
Yeah, probably. But it's one of those, they didn't tell, like they told him it was a bomb, and they told him, you drop it, and then you get out. Do not fly over, it was you
Why did they
immediately
tell
turn and just go, book it. You want to put as much distance between this spot and your plane as much as possible. It wasn't even a, don't drop it and just casually turn around. No, you drop it and then go in one direction to get away from it as fast as possible. Because they didn't want them to panic whenever they know what it was. So it was one of those, it's a bomb, it's a new type of bomb. Just drop it and then run.
The people that dropped, the higher ups that knew what the bomb was, they probably didn't expect him to live, did they?
No, they wanted the Americans to live, but they weren't quite sure exactly what would happen. They knew in theory what would happen, but they weren't quite sure, like, would the bomb actually go off? How big would it be?
What if it just hit the ground and didn't blow up?
Yeah, so, I mean, it's one of those, they knew in theory what should happen. That's why they told them, you drop it and then you move. You get out of the area as fast as you can, or you just keep going. So the pilot...
Did they test them before they did that?
They test, well, I mean, you can't test,
twice.
like, the entire bomb. So they would test sections of it to make sure it was, so that's the way they
I thought
did
they
theory.
tested it in like the desert or something.
They tested them out there, but it was one of those, I don't think they just like full on drop the bomb to see what would happen, because you don't want to mess up your own country whenever you're testing something like that. So they were tested bits of it. I don't think they tested the full on thing, because they weren't quite sure if it was going to work or not. Alright, we gotta keep going about this. We'll talk about bombs. We'll talk about bombs later on. We have a section talking about nuclear chemistry. We will get there later.
Nuclear chemistry?
We have nuclear chemistry section. We will get to it. Alright, number 4. How did the line spectrum of the hydrogen support Bohr's model of the atom? Quentin, what you got?
The electrons of an atom do revolve around the nucleus of an atom.
Say it one more time. I just couldn't hear you.
The electrons of an atom do revolve around the nucleus of an atom.
Okay, so it also has to do with the energy level, because remember, Bohr's model says specifically you're basically stuck in a rut, or you're locked into lines around it. And we would see that with the energy, with the line spectrum coming off of the hydrogen. So you're right partially that yes, they were going around it, but it was more of the energy. Alright, number 5. What is the major failure of the Bohr model? Because we know today, Bohr model was accurate for a while. We know, okay, it's not right for all of them. Okay.
I said the Bohr model couldn't picture the structure of an atom.
Good job, containing more than one electron. So it worked for hydrogen, but that was it. So all the others didn't work quite accurately. Alright, anyone have any questions about the homework?
9.
Alright, we can do the dark game as long as we move quickly. So sorry, Jimmy, got stare at the ceiling. So someone remind me.
Next week. Should be after Monday.
There you go.
Did you know that?
Alright, I didn't know if y'all were supposed to know yet or not. Alright, so.
Oh, I don't know if we are. I just knew.
No,
Because I got big bird.
Okay, well, yes, I'm excited that, yes. Jamie, I'm excited to come back. So, well, I just didn't know if y'all were supposed to know yet.
Are you recording?
Yep. Alright, we gotta go.
No, I mean recording Monday. Like you gonna start? Are you gonna stop?
Because Mr. Dassey is going to keep. What did he say he was going to keep it?
Okay, we gotta keep going. You can ask him later.
Can I start since
We gotta keep
my
going.
birthday?
What?
My birthday's November 6th.
Your birthday's not today.
It's November 6th.
It's not today, Ethan. Alright, Ethan, what can be described as a periodic back and forth motion that transmits energy? I'm gonna go ahead and give you German so I won't forget.
Periodic what? Oh, that's a lot.
What do you call the periodic back and forth motion that transmits energy?
I'll pass.
No.
What's it called? What's it start with?
W.
Oh, straight. Very far.
Alright, first person ready to do
Wait,
it.
wait,
Since
wait,
there's
wait.
two of
I
us.
have stuff over here.
First person ready to do it. Should be okay.
Say go.
Go.
Wave.
Wait, come pick the dice.
Oh, yeah.
Write it down so you won't forget.
I know it. I just had a brain fart.
Write it down. It'll help you to remember.
There.
Poor Tyler. Nope, that's Taylor actually.
That's Taylor?
Mm-hmm.
I mean, it's like
Tyler
Johnny
was like not even over there.
Yeah, I didn't have enough space.
Who's
Sorry.
that guy in the middle right there?
Oh, wait, ask me in history. Alright.
Looking spiffy.
Yeah, let's see. It's technically Quentin's turn since Quentin stole it. Alright, Quentin. What is the distance between any two corresponding points on successive waves?
Let's start with
W.
wavelength.
Yep.
He's
What
pretty
a
good.
guess.
It's not moving. I'm sorry. Alright, Chris's turn. Alright, Chris, what do you call the top part of a wave?
Correct.
Good job, come through. What's the bottom part of the side now?
Z2.
Good.
ZZ Top.
He did it.
Is that what you said?
Poor president.
I'm convinced we're aiming for space.
I mean, that was square.
Assassination.
That was square in the face.
Alright, what is the wave's height? It's also measured the wave's strength.
Let's start with
A.
amplitude.
Amplitude.
You have to go down the line and then.
Wait, what? Who was that I hit?
I don't remember off the top of my head.
I said if it was Harrison, that'd be kind of ironic.
Harrison Tyler.
Is that Polk?
I think it's Polk.
Oh, don't even go there. You want to aim over there?
Nope. Alright, Quentin's turn. Alright,
If I
Quentin.
went Abraham
What
Lincoln, that'd be kind of
is...
ironic.
Alright, make sure you're not getting distracted. We got to go. What is the name, or what do you call the number of complete waves that pass the point by a given time?
Let's start with
F.
frequency.
Hey, Mr. Rhythm Fall. Hey, good job. Alright,
10 and
Chris's
8?
turn.
Or 10 and 1.
19.
Alright, what is the SI unit of frequency?
Let's start with.
H.
First we said H.
H.
Like, is it a letter?
It's the SI unit of frequency.
Technically a name.
It hurts.
Hertz.
It hurts.
Just make sure you don't forget the real definition. Okay. I'm telling Mr. Keys if you did it wrong. Alright, Ethan's turn. Alright, Ethan, what do you call the rate at which a wave travels?
Let's start with
It's not the answer. It's not the answer.
What is the rate at which a wave travels?
Let's just start with
S.
speed.
Speed.
I didn't even hear him.
I was like, why?
I thought it was
What?
frequency.
No, the rate, that has another way of like how where it's
The
moving.
amount of waves through a certain point is frequency.
Yeah. I'm sorry, Ethan. Alright, what's the symbol we use to represent wavelength?
Let's start with
It's like the upside down Y.
Go fast.
Just an L.
Ow.
Lambda? No.
Yep, lambda.
What?
Yeah.
10.
Gavin hit the bullseye, I think it was yesterday.
I think I hit
And it was it then? Who was it? There's someone else hit the bullseye too, right?
Like he got it dead center in the red.
I think I just hit bullseye and
So you got
slid
50?
down.
Yep.
Or is that 100?
I think that one's 50, and then the blue around it is 25.
Interesting.
Alright, so who came up with the particle theory of light?
First name starts with an I, last name starts with an M?
Yes.
Isaac Newton.
Good job. You said M, right?
I said N.
Okay,
I
just wanted
thought
to
you
make
said
sure.
M.
I was like, I heard M, but I'm pretty sure you meant N.
Does that count for something?
Hell.
Nope, doesn't count for anything. Alright, Ethan, who came up with the wave theory of light?
That's
Start
still.
with.
What?
Let's start with.
Last name has been H.
Christian Hamburg.
Hamburger?
I didn't say hamburger. I said Hamburg. Or Hamburger.
I don't think I
No. Hold on. Christian
Christian Hamburger Helper.
Christian Haber?
Haber?
That's so far away.
No, it's not.
It is
You
for.
have like the
I-
first 2 players.
If no one gets closer.
Okay, oh yeah, if
Well, I
someone
know
gets
it.
closer.
I know it,
then
yeah,
you
so-
give it to them.
So,
Alright, for person, raise your hand.
I don't
Wait,
really
last
care.
one.
sorry.
Yep.
Huygens.
Huygens.
That's so crazy.
Huygens. Huygens. Christian Huygens. Alright, Quentin's turn now. Alright, Quentin, who came up with the electromagnetic wave? Because you stole Ethan's.
Let's start with
His last name begins with
That's cheating.
M.
you know.
M.
You came up with what?
Electromagnetic wave with them oscillating at right
What's his
angles.
first name, start with?
J.
J?
J.
A has a middle name.
He does, but you don't have to know middle.
What's it start with?
C.
Steve?
Oh.
C, it's an M?
Steve?
What?
You said Steve.
Alright, last name starts with M. First, raise your hand.
Wait, why? I didn't guess. Oh wait, was that his question?
Yeah, it's Quentin's real question. Go. Alright, Chris.
Martel Webster.
You go with Marshall Webster? No, real? Okay. Ethan, right here.
Mario.
Nope. Alright. James Clerk
I knew that Maxwell, but
James
that's-
Clerk Maxwell. Make note. Maxwell,
Also-
electromagnetic wave. Alright. Who wrote the book Optics? So it's your turn now.
What was that some trouble?
N.
Where's some trouble?
Yes.
I didn't even.
Isaac, do it again.
This is the only 2 I've gotten. Alright.
Some days it's just be that way. That's why
How am I
Ted is
so
far
trash at
over.
this?
You're like 300 feet away. What do you?
Alright,
I'm
what
taller
is the
than
speed of light of a vacuum, approximately? That has nothing to do with that.
3.00 times 10 to the 8.
Good job. Meters per second.
Can you imagine someone's like 8 feet tall walked in here with the head on the ceiling?
I would be impressed.
I wouldn't be.
I would not be impressed. I'd be scared. Why is that dude walking in here?
I'm sorry, I'll get you your money next week. He stepped ahead.
What?
He was ahead of the.
Oh, I had 4 points, and you have
You
like
can go
45.
up to this line.
I have
That's what
0.
said. I've told you before.
Wait,
This is-
I have
yeah,
4
I don't know
points.
why
I
we're
have
saying
0.
This
it's
man
only
already
that.
has like 50.
It's this line.
That's
We-
29.
It's 29.
That's
Let's go.
what's wrong.
Yeah, I don't know.
I thought it was back there at your desk.
No.
I thought it was
I
back
don't
there.
know. We're just
Idiots.
thinking far away on purpose. Alright, what is an arrangement of all forms of electromagnetic radiation in order of frequency and wavelengths?
Let's start with
E.
E?
E. All the arrangement of all forms of the electromagnetic radiation in order of frequency and wavelength.
Wavelength.
What?
Wavelength.
Wave? Did I say wavelength?
Yeah, I don't know.
Wavelength? I'm sorry. Wave?
I don't know if you said it or not. I thought I heard that.
Right.
no.
First, raise your hand. Go. Alright.
Electromagnetic waves.
Electromagnetic wave.
Waves.
What's the second part? Start with?
Is it
It starts
electromagnetic?
with an S.
Oh, I know.
Electromagnetic.
Don't guess.
Wait, the last part starts with an S?
Yes. So electromagnetic is right.
Electro-
That's all of them.
Electromagnetic system?
Okay. I'll let you have it, but if
What?
if
I
he's
got
not
to be
closer.
closer.
He's not closer. Okay.
Electromagnetic spectrum.
Electromagnetic spectrum. So electromagnetic spectrum, that's all forms of it. So kind of like a
It's
rainbow,
my
it's
turn,
all
right?
forms. It was your turn.
No, it was his question, I stole.
You're
yeah.
right, it is. Okay, so it's his, so it's your turn next. Alright, Ethan, come throw your card. Alright, what is
Oh,
the
it's
equation for if you're finding speed of a wave? So they'll use D or speed of light specifically.
Isn't it C equals,
I'm sorry.
there's an F, right?
There is an F.
Is there also a Lamboy symbol in there?
Good job. Is that it?
Yes.
That's it.
Alright, so where's the line?
Alright, the
Put it
line
right here.
is this one.
Easy.
I did not know what I was doing so far. It's okay.
Just sit down, Chris.
Chris, come get your introduction to your face.
At this point, just sit down.
Can't touch your face. Roll. I'm sorry you're upset, but we're rolling. Okay. Watch out for Ted and watch out for my president.
And watch out for me.
Yeah.
Watch out for my projector.
Yeah.
Okay,
Oh.
let's not do that because you're gonna dent the wall for real. So let's not do that. Alright, Ethan's turn. Alright, what is the term we use to describe how
What if it went through the wall?
I would actually
If it went through the wall, you're.
I think I'd
Gamma rays.
Would I be
I
suspended?
think you're still
Would I
okay.
be suspended?
For what?
for breaking, hitting the ball, or
No, your parents would have to pay for it.
No, because we're throwing darts.
Not a little colored duct tape one.
No. If it goes through the wall, yeah, you're gonna have to contact your parents about that one. So careful, don't throw too hard. All right, what is? I totally forgot my question. So it's Ethan's turn. All right, what is it if it interacts with matter, but it also moves like a wave? What is that term we use to describe
Start
it?
with an L.
Starts with W. So it acts like a wave and a particle at the same time.
Wave particle. Particle.
Wave particle.
Particle wave.
Nope, you're right. Wave particle.
Wave
There's one-
particle.
There's one more word.
It's the.
What do you call it whenever you have two people singing together?
A quartet.
I'm about to say a quartet, but
No, that's four.
that's four.
Yeah.
Four.
What's start with?
D.
Diatet. No. Hold on. Wave particle.
It's both at the same time.
We've been here for so long. Can we please just move on?
Wave particle. Dialect.
Okay, I'll let you have because it is a hard one, and this is a newer term. All right,
Can I
wave
please say?
particle.
Please
Yes.
say? If I do it, can I throw?
No.
Wave particle duet.
Wave particle
Oh, duet.
duality is the technical
Duality,
final word for it. So wave particle duality. Watch out for my wall.
Come on.
Stand back there and throw.
Not too hard. All right. What do you call the tiny bundles or packets of energy?
Depression.
The board's all scratched.
Let me start with
It starts with a P.
proton.
Depression.
Protons?
Protozoa.
You say protozoa.
Yeah,
You can't say P words. Not all P words are right.
my man.
But like into the tiny bundles or packets of energy. Alright, first restoration.
Photons.
What?
Photons.
Photons.
You just gave him the answer, Ethan. You're a failure.
I already know that. You don't have to tell me that.
Hey. Oh. Okay, well, at least you got some.
It's like everyone.
This
on
thing
our
is hanging on sideways.
That's everyone in our basket games. When Daniel makes a shot and then I go and I break a shot. Hey.
Alright, we gotta go. Alright, so what do you so if I increase the frequency, will the energy of my photon increase, decrease, or stay the same?
Say it again.
If I increase the frequency,
It'll go up.
it'll go up as well, because it's directly related to frequency.
I mean, it's already.
Alright, not too hard. Careful. Not too soft.
Wow.
Don't dip my wall.
This is ridiculous.
Don't dip my
It
wall.
goes exactly for the wall.
Alright, watch out for Ted. Careful for Ted. Ted
Don't
gets
break
expensive.
it.
Ted's $200 minimum.
200. I can tell you, Rich.
Get off it.
Alright, I think we'll go one more time and then we'll stop.
You
Alright.
might have given me a hand, Ted.
So, what is a device that's used in the laboratory to separate the colors?
Sorry.
S.
What? What's a? Say it again one more time.
What do you call the device in a laboratory that's used to separate the colors?
It starts with an S.
Yeah.
I'm confused. Speed.
Speed.
Alright,
Right,
go
first
for it.
raise your hand. Go. Chris.
Spectrometer.
Spectrometer, but yes.
I was saying it.
It does look like spectrometer, but spectrometer.
It's like how you guys say it, Anglican, but it's actually Anglican. Yeah,
What's the correct pronunciation, Chris?
Anglican. I'm actually about to cry.
I'm sorry. I don't know why.
The blue ones are doing it now. Probably because we broke them.
Sorry.
Yeah.
They are fracturing. Like if you look at the magnets are chipping away.
Yeah, just
So
like my
I don't
soul.
know- I don't know how.
For real?
It's fracturing like my soul.
Okay, not for real.
For real.
No. Alright, Quentin's turn. What do you
So I
call
get
an
another question. I
arrangement?
get a question too, right?
Yes. What do you call all arrangements of the forms of electromagnetic radiation in order of frequency and wavelength?
Let's start with
E.
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 Say it one more time.
An arrangement of all forms of electromagnetic radiation in order of frequency and wavelength. I'm pretty sure I asked
Have
this
we had
earlier.
this before?
Yes, I'm pretty sure I.
Electromagnetic spectrum?
Yes.
What?
Electromagnetic spectrum.
Even Abraham Lincoln's like, bruh.
Imagine that came to life.
I would freak out.
I would.
His stick.
Yeah, I don't know. He must have like the perfect like arch to have it to stick onto it. I don't know. I'm sorry. All right. So What do you call
Sit
the
down.
tiny bundles of packets of energy, of light? It is your turn.
Oh, come on.
I know.
Photon.
Yeah. There.
It's a cosmic
Why do they
photon.
get the easy questions?
I'm sorry.
At least your darts stick when you throw them.
Mine don't stick
It's
at
right
all.
here,
What are you
right
talking
here. It's like
about?
right
It's this line right here.
The darts don't stick with me at all.
Bruh.
Just sit
I'm
down.
very sorry. There's nothing I can do for that.
What?
I'm sorry. I'm very sorry. Alright, go ahead and add up your points. Quentin, how many do you have?
58.
Anyone have close to Quentin?
I have
I
0.
don't think anybody else has any.
I had 8.
Very-
Oh, that's right. you
I'm
did
sorry,
it.
Quentin. Well, I'm sorry, everybody else. I'm happy for you, Quentin. I just really like you today. Alright, go ahead and take out one piece of paper, a pen and pencil. We only need one today because it's actually a printed one. Alright, so one piece of paper, a pen and a pencil.
Do I have
Don't
to
need
take
a
the quiz?
calculator. Welcome back, Amy.
Nice.
One piece of paper, a pen and a pencil. Here's the equation. Anyone have any questions about the equation? Equation.
Wait, what question? Say it one more time.
Alright, so if you're finding the speed of light or the speed of a wave, it's the V or the C, you're talking about speed of light specifically. And then lambda times F.
C equals H.
All you need is a pencil and a noose.
H F.
No,
It's
no.
an H. It's not
Don't make
an
jokes like that. Alright, once you get your quiz, you may begin,
What if I don't feel like it?
and then fail.
Then you're gonna fail.
Alright, read through it. So be careful that first section. First section is completion. Write the words that best complete the statement. Pay attention to what you're doing. Second part, multiple choice. Pray hard and guess if you don't know for the letter of the correct choice in the blank.
What's today?
Today's 30th.
Oh, wait.
Apparently it's mad about being used today.
Huh? Oh,
You okay there?
I'd say there's two of the same question, but it's not the same.
Yay!
Number 1 and 7.
Yes, they're not the same question. So read through it.
You can't explain the particle theory of light, can't you?
You just need to know who was proposed by
I know, but can you explain it?
particle theory of light, but light's made up of like little BBs.
What is the last one?
Nope, can't do that. 1 in 4 chance of Ethan, 25%.
I have a general idea, I just am not too sure about it. Come on, you get gives what it starts with.
No, not for quizzes or tests.
Only for exams.
Ooh, how much time we have?
I can give it another minute or so, but I mean, just pray and guess. more time. Alright, we can't go over the answers just in case Jimmy hasn't taken it yet, so ask me after class if you want to know something. Alright, go ahead and take out your textbook. Turn over to page number 98. So that's where we left off. Thank you.
What are we trying to get to today?
What?
What are we trying to get to today?
You find out?
I'm
Alright.
trying to figure out who did what.
So, we're learning about the Bohr model of the atom, and we started talking about the different models of the atom. Now, keep in mind, we're talking about J.J. Thomson. What did J.J. Thomson say that the atom looks like? Chris?
J.J. Thomson?
Yeah.
A cookie.
Yeah, so the plum pudding model, that was his model. Now, they discovered that's not quite right. And then you had Ernest Rutherford. What did he say the atom looks like? Ethan?
I don't know.
Alright, he said that they're locked in like planets just looping around. Well, there's a couple of problems with it, and your book starts to explain it as well. That physicists knew that, okay, if that is really happening, then you should have the electrons start to lose energy as it circles the atom, and you should start to have it slowly condense towards the center until it eventually basically crashes into the nucleus and explodes. I love this moving diagram. This is my favorite diagram in the entire year because whoever designed this had so much fun apparently just being extra with it. So that's what physicists knew, that as you have the electron, it should be giving off energy, and so it should eventually collapse towards the center of the nucleus, and it should explode basically and rupture itself. So I don't know who designed it, but they had fun whenever they designed it. But that's what should happen. Physicists knew, okay, if you have it orbiting like that, it should eventually lose energy and collapse in the center. But it doesn't do that. So physicists knew, okay, it doesn't do that, it stays in its spot. Why does it stay in its spot? What's keeping it stuck there? So they want to know, okay, why is it staying in that one spot, and why is it not collapsing towards the center like we expect it to? So they knew we have to come up with a better model. The Bohr model, or the plan, so they knew that the Rutherford model works to a certain extent, but it doesn't account for everything. So they came up with the Bohr model next. The Bohr model was come about by studying with hydrogen in particular as to why hydrogen gives off energy and gives off light. And that's what they were looking at to try to figure out what's happening on the inside of it. Oh, and as a side note, your book has this diagram at the top of your page as well, showing off with photons energy. This is one reason why whenever you light metals on fires, pure metals, they glow specific colors. Because you have a photon of light strike the atom, and the atom becomes excited. It doesn't like that extra energy. So it's unstable, and so it wants to get rid of it. Whenever it kicks off that atom, it kicks it off at a certain frequency, and that's how we see it as colors, as it turning certain shades of blue or purple or orange or red. That's one of the labs we watch later, is they light elements on fire to see what colors they glow, and that's the reasons why for it. Alright, so your book points out with the Bohr model of the atom to help explain why do we see hydrogen in particular give off the lines that we see in the line spectrum. Alright.
So when I'm touching this, I'm like killing atoms.
I mean, not killing them because technically they're not alive, but they're smashing. I mean, you are condensing. Technically, it's the electrons pushing back against your electrons. Technically.
So there's just so many of them that this is solid now.
Yep. And there's so many of them, but remember, there's a lot of empty space, but there's so many of them there because they're so tiny.
It's like, how many of them like are on like one sheet of paper? Like billions?
I would say probably trillions. There's a lot. Alright, we gotta keep going though. Alright, so just make note the electron and the hydrogen atom can move about the nucleus only specific energy levels. So that's what Bohr was coming up with saying for his, that okay, they must be locked into a spot or into an orbit. That's why they're not moving, and that's why they're not falling. How many of you have started practicing driving, or you already have your driver's permit?
Starting the practice.
Alright, how many of you, if you've driven on older dirt roads, you'll notice they have those ruts in the roads? Alright, what happens if your tires get basically aligned with those? Anyone know what happens?
You get stuck.
You get stuck. Now, can you get out of the ruts easily?
Yeah.
Depending on what type of car it is and how deep the ruts are. If it's like an old dirt road where it's been driven over and over and over again, those ruts might be pretty deep. So it's the idea though, once you get in it, you have to use your car to get out of it. You have to use energy. Now you have to be careful because you don't want to overshoot and end up in the ditch or end up off the side of the road. But it's the idea, you want to be careful because you're getting out of it. That's the same idea. He's saying that, okay, that the electrons, they're in these ruts, or they're in these energy levels, and they're not moving out of it. He's saying that the energy of the orbits is quantized, with the idea of it, you have to have that quantum of energy to move from one area to the other. Now, you have the nucleus of the atom, and you have these orbits around it, that the electrons, as they're moving around, they're stuck in these orbits, or stuck in these orbits. And to go from one energy level to another one, they have to lose or gain energy. The lowest energy state is at the ground level, so that's the closest one to it. So picking up the lowest energy state or the ground state, that's whenever you're at that lowest energy level. That's whenever it takes the least amount of energy to stay there. It takes more energy to move farther and farther and farther away. Partly because of the charges of the protons in the center and with the electrons. To move farther away, they have to gain energy to basically jump from one to the next. Your book describes it as climbing up the ladder. Alright, how many of you know someone that's like deathly scared of heights? Alright, so if you've ever watched them whenever you're going up in an elevator or an escalator, or if they have to go somewhere where they're near an edge, you'll notice that on the ground they're probably okay and they're probably pretty calm. But as you get higher up, they become more and more excitable or more nervous. And if you've ever watched videos of like, oh, have y'all seen the videos of, I think it's the bridges in like China and the other areas
Clear
in the
bridges.
Orient where it's the clear ones? You watch people on those, it's hilarious. Oh, they're so long in a lot of cases. But yeah, the people that are like straight up crying because they're so freaked out because they don't like it. How many of you are scared of heights that bad? I'm sorry, Chris. What says high as you've ever been? Oh, like besides like an airplane.
Like 400, 500 feet up.
I'm sorry. So,
I was in the Arco in St. Louis.
oh, that's cool. I went there, but we didn't go up to the top because it was already closed by the time we got there. We barely missed it.
I've been there twice. The first time it was closed, and the second time it wasn't.
It was fun, but it made you nervous to get to the edge. I mean, it's okay.
Yeah, like I'm not deathly scared, but I don't like them. Like I pass out on roller coasters. Like literally any roller coaster, I hit a roller coaster and pass out.
Is it the blood flow or is it
I
just?
have no idea. I just pass out, and I feel horrible after. But yeah, I passed out, and I don't know if it's the heights, but yeah.
Yeah, but that's part of the reason as to how come if you know someone that's scared of heights, they become more excitable the higher up they get. That's kind of like the same idea if you want to think of it that way. That the higher up or the farther away from the nucleus the atom is, the farther away from the nucleus the electron is, the more excitable it is. It has to have more energy to get that far away from it. It doesn't like being far. It wants to get back towards the nucleus as best as it can. Speaking of that, of the ground state, that's whenever the atom is as close to the nucleus as it can get for it and not be like in the center. Then now any state above that is called the excited state. So it has more energy. The atom is there. Excuse me, I keep saying atom. The electron's there, but it doesn't like being there for it. Your book compares it to climbing up a ladder to where you have to stand on one rung typically at a time. Now most of you, whenever you're climbing up a ladder, you'll shift your weight from one foot to the next foot as you're going up, but you can't hover in between the rungs of a ladder. Why can't you hover in between the rungs of a ladder, Ethan?
Just can't.
Yeah, you can't because gravity says no, you can't do that.
I mean,
And it
technically,
pulls
you
you
can't
out.
hold yourself up.
You could, but electrons aren't smart enough to do that. So it's the idea of, okay, as you're going from one energy level to the next, you have to be fully going from one spot to the
I
next.
hate ladders.
So that's the, wait, what?
I hate
Why do you
ladders.
hate ladders?
I just hate 'em.
Do you fall off them a lot?
I'm not deathly scared, like Chris said, I'm not like that scared of heights, but I hate ladders and cranes.
Sorry. But yeah, it's fun. No, ladders make me nervous because I have siblings, and that's why ladders make me nervous because siblings would be mean with the ladders and start shake them to a
Beat you with the ladders.
No, they would like
Oh.
shake them while you're on them and stuff and being like, oh, I don't know if I think it's broken. Stop it. Leave it alone. Stop touching the ladder. It's that's the reason why ladders make me a little nervous. It's not the ladder, it's because of memories
Past
of
trauma.
being on ladders. Alright, well that's the idea behind it. Take a note though that the idea of the electrons are locked into these spots. They can't hover in between them. So it's like climbing a ladder, you have to be fully on one or using your arms. You have to be fully on one. But that's the idea of it can't just be in between them. It has to go fully from one spot to the next spot for it. Alright, your book points out the lowest energy state possible is the most stable. The electron wants to get back to that as best as it can. And that's one reason why whenever it kicks off the energy, it tries to be stable. So for it to go from here back down to a more stable spot, it has to lose energy. Whenever it gets rid of that energy, it'll throw it off as a photon. And so we see that energy typically as light. And that's what scientists were looking at whenever they were looking at the hydrogen spectrum. They were looking at the lines from the line spectrum, and they were noticing, okay, why do we see it as different energy? Alright, does anyone know which color of the rainbow has the most energy?
Red,
Not red,
purple.
purple,
Blue.
or violet. So,
Oh, I said it.
you did. So red has the least amount of energy, and then blue and purple technically violet has the most. So that's what they were looking at whenever they were looking at the line spectrums. They were noticing, okay, that you have the infrared category, the category that we can't see, but that is the lowest energy level. That's whenever it's not using a whole lot of energy because it's moving a small distance. The medium level, that's whenever we start to see it with the line spectrum. That's whenever it's losing more energy because it's following a greater distance. And then also in the ultraviolet section, which we can't see again, that's whenever it falls the most because it's losing the most energy. Your book compares it to rolling bowling balls. Alright, if I were to put a bowling ball on this table, and I'm not going to do it because I like my floor, but if I were to put a bowling ball on this table and then roll it off onto the floor, what's the bowling ball going to
I'm
do?
a past state champion in bowling.
Okay, and then what would happen? I'm just gonna let that go.
Okay.
You're not distracting. What's gonna happen, Chris?
It's gonna hurt
Hurt what?
the floor.
Yeah. Now, what would happen if I were to hold it as high as I could and then drop it? Would it make a louder noise or a quieter noise?
Wider.
What?
What?
A lot of them.
Louder. Why?
No, like, it's higher.
Yeah. Why? You said, if you think it's gonna be quieter, why?
Because it's higher.
Okay, why would it make a quieter noise if it has more energy whenever it falls and hits the ground?
So energy doesn't exist.
Good. Alright, so just make a note though for the correct answer for your knowledge. And just make a note that, okay, yes, if you fall shorter distance, you're gonna have some energy released as sound. You might feel it with vibrations. If you have more energy released with gravity, if you drop an object, you might notice it more. But if you were to combine them and have the most energy, that one would have the most energy loss. Kind of like if you were to jump off buildings. You were talking about jumping off buildings the other day. If you were to jump off the roof of this school, I don't know. You were talking about the other day. If you were to jump off the roof of this school, what would happen to you, Ethan?
It hurt.
You know, what happens if you were to jump off the Empires? What happens if you were to jump off the Affluent building?
It hurt.
It would hurt for a brief second, and
It wouldn't
then
even
I don't know
What?
if it hurt at all,
What?
so you may die before you hit the ground.
you might pass out before you hit the ground.
And then you die.
Yeah. All right.
But question.
Okay.
I'm not being. You know when 9/11 happened?
Yes.
The water, was there like water nearby the towers? Did anybody make it if they jumped? Nobody did?
It was too high up. When you hit the ground, when you hit the water 50 feet up or higher, it feels like you're hitting concrete.
Yeah. For them, they just didn't want to be trapped in the burning buildings. That
That's
was
why
one
they
of
jumped.
those. Yeah. And so
I
it's
gotta
one of
jump.
those. They knew they were about to die, and they would rather die by impact than
Where
die
would
by
you rather
burning.
die Well, they also they didn't feel the impact. They passed out before they hit the
Yeah,
ground.
but it's one of those like they knew they would die whenever they did that. So it's one of those. That's why that was very, very dramatic. Is because people were seeing them jump off the building, but there was nothing like anybody could do for them. Okay.
What's my favorite?
You need to.
What would you rather do?
Oh, that's. I have 10 minutes. We gotta hurry. We can talk about stuff, so we can't keep talking about it. But that's the idea of, okay, the higher the distance is whenever you're falling, the greater the energy on your body whenever you actually hit the ground. Now, you will pass out depending on how high you are, but it's one of those where, yes, there is more energy in it. So that's the idea from it with the electrons. Now, they kick off energy as photons. Listen, come on, the more energy, it's either as violet or ultraviolet, which we can't see anymore, or it's in the infrared or the red category. Alright, so anyone have any questions about that idea?
I'll go home.
Nope, not yet. Alright, so that's the Bohr model. The Bohr model works for hydrogen, but it didn't work out mathematically for the rest of the electrons. So scientists knew, okay, he has the right idea, but it's not quite right for everybody. So this is partly right, so we need a little slightly better theory to help it out as well. Louis de Broglie, make a note for him. He came up with the next idea on page 100. So Louis de Broglie, he
De
proposed Broglie. So like you're saying Mowgli,
Rockland?
no, Broglie. Like you're saying Mowgli with a B. Broglie. So he came up with the idea of matter waves. This is whenever it starts to get a little trippy in
Trippy
chemistry class because it's going to get more abstract. And your book talks about this later on, that some of it, this is our best explanation, even though it doesn't make a whole lot of sense. It is abstract. This is our best explanations at this time. So this is whenever it starts to get a little bit weird. Alright, so light acts like a particle in a wave. What do we call that, Chris?
Particle in a wave.
Yep, what do we call that property?
Duality.
Duality. And so they said, okay, if light is made up of photons that act like particles in waves, and electrons, they're also very small, so what if electrons act like particles and waves too? What if all matter acts like waves and particles at the same time? So he proposed that since radiation has properties of particles, then particles in motion should also have properties of waves. Basically, he's saying that, okay, if you have an object like, if you have an object that is made up of matter, whenever it moves through space, it should move in a wave pattern very, 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 very slightly. This actually really does happen as far as scientists can tell. Just most objects are so large that we don't notice it. That their wavelength is so tiny, we don't pick it up. But since an electron is so small, you can notice its wave pattern a lot more. So it's a little bit trippy to think about how all objects move in a wave-like pattern, even though we don't see it do that.
So wait,
So
that table's moving in a wave-like pattern.
it has to be object in motion. So if I were to take my piece of chalk and throw it, technically it's moving in a very slight wave pattern, but you can't see it.
Like everything is like, so if I were to go like, that's a wave pattern.
If it's object in motion, yes. Now, it's such a tiny wave motion that your eyes don't pick it up and we don't ever notice it. But if you were to throw a baseball, it would be moving in a very slight wave pattern. But again, because it's so small, your eyes don't notice it, machines don't notice it. Your book points out though that if you throw a 5-ounce baseball, if you throw it at 110 miles per hour, that it has a small wavelength. It's 9.3 times 10 to the 23rd picometers. That's 1/1,000,000th of a meter. So it's very, 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 very small. But since electrons are very, very, very small, we can notice it with theirs. Okay,
Do humans move in a wave-like pattern?
if you're moving, yep.
It's just like super, super small.
Yep. It's one of those to where it gets kind of trippy and kind of weird because we don't notice that. But that's what he's proposing. So, make a note of that. So, with the matter waves, he's saying that basically everything moves in this wave-like pattern. Just the larger the object is, the less we notice it. So, but since an electron is so small, it moves in this wave-like pattern around the nucleus. We call that matter waves. So at least the term makes sense. So all matter moves in a wave. So he proposes it, matter waves. Make a note for that one. Alright, so your book is also pointing out that this also helps us to see that, okay, that the electron, it can behave like a wave and a particle like light, like photons at the same light. So it has that same wave-particle duality with the electron. Where it has substance, it's made up of matter. This is why Chris can't go through his book like he was poking at earlier. It has substance. But whenever the electrons are moving, they're moving in this wave-like pattern around the nucleus. But that's one reason as to how come we can take electron microscopes and take pictures of very small objects, because scientists notice that electrons, they can be diffracted by a small opening. Anyone know what diffraction is? I know this is not physical science, but we talk about it in physical science. Alright, Chris, what's your hand first?
Something reflecting off of
Diffraction, not reflection. You have a small opening and you shoot light through it is how we typically notice it, but what do we call it whenever you have a diffraction of an object? Right?
It like bends.
Yep, it's bending. So they would notice that, okay, if they shot a beam of electrons, that it would be diffracted or bent by nickel crystal. So they were noticing, okay, so diffraction, we notice it with light spreading out through a small opening. So they were noticing, okay, electrons do this too. So they must also have this wave pattern, kind of like how light does. So they were noticing, okay, there's similarities between it. Because of that, we can take electron microscopes and take images of very small objects. So your book shows you, as shows you at the top of the page, the similarities between an X-ray diffraction and electron diffraction, how similar they are. And then it shows you the kind of creepy picture of a scanning electron photograph of a moth. They can use the electrons to basically take a photograph of something, and so that's what a moth's face looks like. And I guess it's kind of cute, sort of.
Huh?
Kind of, on page 101. Kind of cute, kind of not, but that's what a moth's
So I
face
don't like
looks
those.
like. Wait, raise your hand.
That's why I don't like bugs.
Yeah, it's one of those, you're gonna go, ugh. But yeah, so that's what a moth looks like, but you have to use the electrons to take photographs of that. Alright, so checking out the wave-particle duality of nature applies to all waves and all particles, although for macroscopic, larger objects that you don't need a microscope to see, we don't notice it because the wavelength is so small. Alright, Schrodinger's equation. Your book talks about this very briefly because the equation is super complicated for it, but it's the idea of a standing wave for it. So, Erwin Schrödinger, take a note of him, he combined the Bohr model with Broglie's model to propose the wave mechanical model, also known as the quantum mechanical model. What they said is that, okay, that you're going to have an electron with an orbit, but it's going to have an integral number or a whole number of wavelengths in the orbit. So as it's moving, it's moving back and forth in this wave pattern, but it has to be a whole number, because if it's a fraction, the waves will cancel each other out. So how many of you have tried to do like a lasso before, like take the rope and make a lasso in the air? Right, you able to do it?
Yeah.
What happens if you got out of sync with it whenever you were trying to do it?
The circle part looks weird.
Yeah, it starts to like get all wobbly and then it collapses if you don't do it properly. So that's the same idea, is you have to have those even numbers or whole, you have to have a whole number of waves as it's moving around, otherwise it won't work properly. So that's what he's saying is, he came up with the idea of a standing wave. A standing wave is more of a physics concept, but it's the idea of the wave is moving back and forth, but it looks like it's not transmitting energy, so it looks like it's standing still. So it's kind of a trippy idea, But that's what he was coming up with the idea of saying, okay, if you have a standing wave, it looks like it's standing still. Now it's still moving, but you don't notice it anymore. So again, kind of a weird one. Your book talks about his equation, but even your book says it's too complicated. We're not going to worry about it in high school. So it's complicated. Just note though that he came up with the standing wave. All right. Anyone have any questions though about that one? Now he came up with it, and he actually used the Schrodinger equation to describe electrons and even the largest atoms and even in whole molecules. But again, because this is high school, you don't have to know the equation. If you want to look it up, go for it. But it's one of those you'll realize, whoa, that's intense. But it's more of a physics concept, and you'll get to it in higher levels. All right. Anyone have any questions about Schrodinger's equation? All right. Or Schrodinger is with the idea of the standing waves with the wave mechanical model. Okay, I can't do anything in 2 minutes. Alright, we'll stop there. Remember for tonight, read pages 103. Okay, we'll probably get a little bit farther to 105. So 103 to 105. It's gonna get a little bit trippy. Yeah, this is where it starts to get a little bit weird. But this is our best explanations for stuff. So page 103 to 105. Answer on page 105. Number 2. And then 6 through 8. So number 2 and 6 through 8. And then
That's enough.
we're gonna go a little bit further.
Nah, that's enough.
Man, we can stop there. Okay, but just make sure that you read page 105 because I'm probably gonna start that on Monday. Alright, so read pages 103 to 105. Be sure you are reviewing. Alright, so thinking back over it, who came up with the idea of you have energy levels with the electrons going around it, that they're locked into those orbits? Who came up with that model? Bohr. There you go. Alright, who came up with the idea of matter waves? Anyone remember?
What's the
Last one is with B.
board?
Nope. What?
Brokaw.
Broglie. So Louis de
Broglie?
Daniel Broglie.
Broglie. Alright, who came up with the wave mechanical model and the idea of a standing wave?
Stroganoff.
Schrodinger.
Stroganoff.
Schrodinger.
I love Stroganoff.
Alright, so Schrodinger, what do you call the lowest energy state of the Bohr model? So whenever it's the most stable. Ethan?
Ground phase.
Good job. What do you call any state above that?
High place.
Excited state.
High place.
Alright, have a good